We can start at the other end of the mechanical chain by measuring acceleration and integrating to get velocity and position, instead of measuring position and taking derivatives to get velocity and acceleration. Now, how can we measure acceleration? It's going to definitely involve our understanding of F equals ma. And the simplest way is to employ a good old-fashioned seismic transducer. Initially, these big transducers were a chunk of mass mounted on a spring and a damper. And if the mounting was subject to an acceleration, then the mass would take some time to respond because of its inertia. So it would compress the spring and the damper, and the motion of the mass would depend on the acceleration of the element below it. And these were seismic transducers, primarily meant to measure the accelerations associated with earthquakes, for example. Now this one is a single axis transducer. It's got a mass and it's being subject to motion in the vertical direction here. It's possible to make multi-axis, three-axis seismic transducers, which would have springs mounted out in this direction and also out in the third dimension, dampers as well, so that you could detect motions not only up and down, but side to side and into and out of the display. Now, to function effectively with the usual kinds of larger components that we can manufacture in traditional mechanical engineering fashion, this would have to be a fairly large, heavy mass and a fairly large, heavy transducer. And it's going to have a really low natural frequency. So we're going to have to do a fair bit of calculation to pull out what the acceleration information is. But we can apply the same sort of behavior, same sort of calculations to a much smaller version if we build it in silicon on an integrated circuit. Now it's important to point out that because there's a mass sitting here, it's going to be subject to motions associated with acceleration of the housing that it's in, and also it's going to be sensitive to gravity in the vertical direction. So all of these acceleration measurements are going to measure acceleration plus gravity. Or in an axis that's oriented horizontally, it'll just measure the acceleration, the motion due to acceleration. Now this is an example of a chip that we're going to use in the lab. This is a micro electromechanical system, MEMS accelerometer. And what that micro electromechanical system means is that integrated right here on this integrated circuit is a mechanical element with the seismic mass in it. So that when this is accelerated, there are actually forces generated inside here on this little mass that's too small to see. This is a 3-axis accelerometer. It's got a range of plus or minus 3 Gs, and it has analog outputs. It's from a company called Analog Devices, the same people who make the TMP36. And we'll put voltage in and a ground connection, and we'll get an analog voltage out for X, Y, and Z components. Now that analog voltage will have to be calibrated by setting up the accelerometer so that we know just what analog value corresponds to 0 and just what the sensitivity is, because it will vary. Now, because this is a small system, it can give you a fairly high frequency response. The device in this one has a 5.5 kilohertz natural frequency. So at any considerably lower frequency, it's going to give you performance that's almost instantaneous in terms of its response. The advantage of a system like this, very simple, very little programming involved. We can connect these outputs directly to analog inputs on our microcontroller or to any other system that needs some sense of what the gravity is. This device, it's important to know when you go and work with it in the lab, takes a 3-volt input maximum. So the supply side should be anywhere between 1.8 volts and 3.6 volts. So make sure you don't connect that to 5 volts or you'll tend to damage the chip. The next one we'll look at is a similar chip. This is the LIS3DH, similarly priced, both of these well under $10. And this is another micro electromechanical system, but it has digital output and provides 3-axis acceleration measurements. The big advantage of this one is because it's a digital system, it's communicating over either I2C or SPI digital interfaces, and that means that we can put some settings into it and then collect digital data out. So we can set this up to have different output scales depending on what sensitivity we're looking for. We can select these from our microcontroller at either 2G, 4G, 8G, or up to plus or minus 16G. Our data output will be in integers and already pre-calibrated. So when we get 0 out, we know it's 0. We don't have to worry about doing our own calibration because the device has been calibrated from the factory. It'll give us digital output at up to 5 kilohertz output rate. And so we can resolve frequencies up to 2.5 kilohertz in our accelerations. That would correspond to, for example, the frequency associated with 150,000 revolutions per minute. So we're talking about some fairly high vibration frequencies. Now we can make measurements of acceleration with this device and detect a variety of things. We might want to detect whether something's moving. So if we want to know systems are in motion, we can activate various functions based on detecting the current acceleration. If we're continuously detecting gravity and suddenly we detect no gravity, we've got an immediate indication we're in free fall. And whatever this device is, we'd better do whatever we can to protect it before it hits the ground. If it's a hard drive in a laptop computer, we could at least park the hard drive heads before it hit the ground. And that would be a considerable advantage. We can also measure taps on the device by detecting the acceleration when you tap your fingers on it. So there are a whole lot of capabilities that we can get out of these accelerometers, including orientation simply by measuring which direction is gravity, or a bunch of input devices for virtual reality and gaming. The applications are enormous, including simple old-fashioned vibration monitoring for mechanical equipment, where we want to detect if something's vibrating, how much it's vibrating, and be able to do some diagnostics on the equipment from that. If we, instead of making an accelerometer like this one, which senses linear accelerations, we could make a rotational accelerometer that would sense rotational accelerations. And these are typically referred to as rate gyros. They're really not gyroscopes because there aren't rotating elements in them, but they are detecting the rate of rotation in a particular direction. And if you combine a rate gyro with an accelerometer, you're getting considerably more information. You've got 6 degrees of freedom information about how these things are moving. Here's an example of a companion device to the accelerometer. Same kind of footprint, but it allows you to detect rotation rates in degrees per second. Also an I2C output, also 16-bit data. And when you combine this with an accelerometer, you get considerably more information, almost enough to have an inertial measurement unit that will tell you which direction your aircraft is flying and how it's moving over time. If we add to that a magnetometer, often built into the same package as an accelerometer, then we've got multiple sense elements that'll tell us which direction we're facing, which direction is down, and give us full position orientation. This can be really useful if you're trying to line something up and maintain its alignment. And finally, if we take all of these pieces and put them together into an inertial measurement unit, or IMU, we'll have an accelerometer that gives us XYZ acceleration in the 3 directions. We'll have a rate gyro that tells us how quickly we're rotating in each of those directions. And we'll have a magnetometer, which gives us compass orientation. If we take a 32-bit microcontroller to do the sensor fusion math, to put all of these together, then we can wind up with absolute orientation of the device, seen down here. And you can see this display on the screen is following the motion of the device as it's moved around in the hand. Now you can package all of these together with a high-performance microcontroller for well under $100 and get output that's good enough for controlling drones or fighter jets or space launches, because this capability vastly exceeds the measurement capability that we had when we were launching major space missions in the 60s and 70s. So the capability of measuring position and orientation has gone up enormously, and the price has dropped also enormously. So you should be looking around for applications where an accelerometer or more complex inertial measurement will give you information in your application that hasn't been applied yet. And building those kinds of capabilities into practical devices will continue to produce engineering advances and new features for consumer products that are going to be very important in the marketplace. So this week we'll be looking at making some accelerometer measurements with this ADXL335, an analog accelerometer. It provides us with the same kinds of capabilities that we can get from this more flexible digital accelerometer, with the simplicity of being able to interface to an analog output. We'll be measuring particularly on the x-axis and looking at accelerations, motions in the x direction, and trying to measure the acceleration, and from that integrate to get position and velocity.